Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Scaling your data infrastructure is hard. Maintaining data quality standards as you scale is harder. DataBand solves this. Their unified data observability platform gives data engineers visibility over their stack without changing existing pipeline code. Get end-to-end visibility into your pipelines and identify the root cause of issues before bad data is delivered. Seamlessly integrate with over 20 tools like Apache Airflow, Spark, Snowflake, and more. Use customizable dashboards to see where pipelines are broken and how that impacts delivery downstream. Get alerts on leading indicators of pipeline failure. Open up your pipeline and see exactly which code strings are broken so you can fix the issue immediately. Create more reliable data products. Go to pythonpodcast.com/databand today to start your free trial. Your host as usual is Tobias Macy, and today I'm interviewing Andrew Ferlitsch about the patterns and practices for deep learning applications and the book that he's writing to help people learn about it. So, Andrew, can you start by introducing yourself?
Thank you for inviting me to your podcast. I'm Andrew Ferlitsch. I work for Google Cloud AI. I'm in developer relations. Prior to joining Google, I was actually in Japanese IT. I worked for Sharp Corporation of Japan for over 20 years as a principal research scientist. And my specialty was in imaging. You could say I was an imaging scientist. Did a lot of computer vision. And, what's really interesting I found about deep learning is everything we do today in deep learning with computer vision, we used to also do it before deep learning, machine learning, but it took like a mass number of people with PhDs and millions of dollars. And what I find just so fascinating about machine learning and deep learning is how that is really scaled way down the cost, the speed, and has really brought it into the realm of, your software engineer can now build and deploy applications that used to take this massive amount of cost and resource.
And do you remember how you first got introduced to Python?
Was probably more accidental. I knew when I first used it was 2016. And I know before that, I would have thought it was just some kind of toy programming language I didn't take serious, I was doing this consulting job with an agricultural technology company, CID Bioscience. They were developing an autonomous farm vehicle that would use computer vision to count crops and, detect infestations in the crops. Okay. And so all the experimental code that they were putting together was in Python. And of course, I had to jump in and participate, so I had to learn Python.
And so now in terms of the work that you're doing with the Deep Learning Patterns and Practices book and your work at Google and your previous work with Sharp, it definitely gives you a good background in terms of the machine learning and deep learning space. And as far as the actual deep learning aspects, before we get too far into some of the patterns and practices, I'm wondering if you can just give a bit of an overview about what are the major elements of a model architecture that people need to be aware of as they're starting down the path of building something with deep learning and thinking about how they want to approach the problem space and approach the actual building of the project.
Well, what we find today in models, instead of sort of being this sort of Wild West graph of nodes, is now there's, formal sections to models, okay, call them components, and sort of a formalization or designs of how to put those components together and how to connect them. And so at the top level, whether you're doing computer vision, natural language understanding, or structured data, you're going to have what's called a STEM, then a learner. And then the last part is the task component, and that's the task you actually want to learn. And the learner itself gets broken down into groups. Those groups get broken down in the blocks. And how they're assembled will really say whether you're doing, say, representational learning or transformational learning, etc. I hope that helped address that question.
Yeah, that definitely is useful because I know that, for people who are new to this field, you hear the terms, neural networks or deep learning architectures, and it's just this, black box, and you don't really understand what are the different pieces to it, but being able to break it down into these are the different subcomponents of the network helps to at least make it an approachable problem of, okay, well, now I know I need these different components to be able to put it together so that you can then direct your research to figuring out how to approach that problem more specifically. And in terms of the specifics of a given task, you mentioned that a lot of the detail you know, for a given project that you're trying to work on is in the learner or the task layer of the network. And I'm wondering if you can just dig a bit more into the relationship between the specifics of the task that you're trying to build for, whether it's natural language understanding or computer vision or image recognition, and the specific architecture and the components that you're pulling off of the shelf for being able to build that full network.
Well, one, we could probably spend a whole hour just talking on that, so I'll just kind of briefly summarize. Over the last few years in the research, we came up with this phrase, you see it, I used a lot, called essential features. Okay, so if you look at a model and you start at the top of the model, and as you sort of work deeper and deeper in the model, and you get near the end before you do the task learning, okay, you have what's called a latent space. It's a representation of the input in a low dimensionality. And what we really want in there are what's called the essential features. Okay. And if we can keep that constrained, we'll prevent things like memorization, memorizing examples, and allow the model to better generalize to examples it's never seen, particularly if those examples are outside the distribution that the model was trained on. So a lot of effort in the last few years is all the different ways to represent that latent space and how to train the model so that latent space just has the essential features. But once you got that, the task learning is simple. And it's actually plug and play. I can take that same bottom part of the model and I can put on a regressor, to say, predict the selling price of a house. I could take that off and put on a classifier and predict who the target demographic is that would be most interested in buying the house. So I don't even have to have two separate models. It really just comes down to really the latent space and how it's trained, what I can accomplish on the other end.
That puts me in mind of the, recent developments in transfer learning. Is that pretty much the exact same thing of what you're talking about, where you're using the regressor versus the classifier?
Before I even jump into it, there's a little humorous part here. I don't want to date myself, but, I got my degree in artificial intelligence, graduate degree in the late 1980s. And when I got out of college, it was the AI winter. So, nothing happened. I'm in a different course. And one of my specialty things was this really obscure statistical area called distributions. And it turns out that deep learning is all about distributions, whether it's distributions in the data or distributions in the weights inside of the model. So suddenly here, 30 some odd years later, what I actually learned in college became important. Okay. Okay, so in transfer learning, it goes into several different directions, but essentially what you're saying is you're either transferring two things. You're either trying to transfer the essential features in the latent space and say those essential features are similar enough to another domain. Okay, for example, let's say I have a model that's learned to tell the make and models of cars. Okay, it's probable that the essential features in that latent space are pretty much almost identical to what we needed for trucks. Okay, so I'm just going to transfer all of that up to the latent space, take my truck data set, and then just fine tune it. In other cases, the transfer may not be related to the latent space, particularly if the data sets are sort of far apart domains. And the other important thing we find in a model is the distribution of the weights in the model. I'll try to keep it simple. When you first train and you have all those nodes and each one has, let's just simplify it, a weight on it, okay? You have to start with some initial value. But if you started with the same value, let's say everybody was a 1 or a 0, their updates would be identical and effectively be symmetric, and it's the same as having a model with just one node. So you have to start off with this sort of random amount, distribution of weights when you train it. And the thing is one random not all random distributions are good. Okay, some are better than others. And the idea, how do I find a good distribution that gives me what's called numerical stability in my model, so that when I train it, I get that convergence on that global or best optimal outcome I can have for that model. Well, in some cases, and that could take a lot of training and experimenting, but if you have an existing architecture that has a highly numerical stabilized weights from previous training, sometimes you just say, that's my initial weight distribution instead of doing a random draw. So that's a different form of transfer learning.
In terms of the numerical stability of a model and trying to optimize that sounds like the hyperparameter search and hyperparameter optimization problem that I've heard a lot about.
Actually, that comes afterwards.
Okay.
One of the mistakes that people were making in hyperparameter search is you take a model, right? So you got this generic architecture and you haven't started training yet. You take a draw from a random distribution on your weights, okay? And then you try to do your hyperparameter tuning. The problem is, why would you do your hyperparameter tuning on weights that are not even stable yet? So first you're going to do all these pretext tasks to make sure you have stabilized weights, numerically stabilized weights. Then you do your hyperparameter tuning.
As far as your experience of working in the space and working with other people on building these deep learning models and applying them to different problem spaces, I'm wondering what you have seen as the sort of overall level of awareness and understanding of some of the different considerations and challenges in the overall life cycle of building and developing and deploying a model among sort of the general community of machine learning engineers or data scientists, and sort of the emerging best practices in the deep learning space.
Yeah, I guess I could cover another hour, but keep it brief. There's always challenges. One area that never ceases to amaze me is on the data side. The more and more data we have, it continues to be a challenge, particularly now that we're on such a large scale. We have to find solutions using that at least at some degree use unsupervised training so that the data doesn't have to be labeled. What are the right ways of doing it? How will they fit into a model that is then later fully trained on labeled data? And then we get to the other end. I got to deploy these models, and I got to deploy them, at a large scale. When you talk about the real world, today models go into production. It's a business. It's an enterprise business. If it's a social media site, you may have, tens of millions of people a day using the site, right? So we're on a very, very large scale. And no matter how you train the model, what data you got, it's pretty much guaranteed that the distribution of your training data won't be exactly the same as the distribution that the model sees in the real world. And so from a statistical point of view, what it sees in the real world is a population, okay? What you're training on is on some subpopulation of that population. And on top of that, you don't have every example in that subpopulation. So it's a sampling distribution of that subpopulation. My real challenge is not to try to get more data, but how can I train it in a way that given this population I'm training on, it will still generalize into that differential between the subpopulation and the population that the model will actually see.
And then within that sort of distribution of that subpopulation, you also have the problem of trying to counteract any potential bias in that randomized subsample of the population.
Yeah, we see all kind of, a few years ago, all kinds of techniques tried that would fail or misdetecting. I mean, first I'll give you a classic example. ideas of how it's done. When they started to first make X-ray classification models, they inadvertently were biased on what's called the view. Okay. Here was a scenario. Most of this data was coming from big hospital groups. And big hospital groups are very cost billing conscious. Okay. So at any one of these big hospitals, you're going to have more than one X-ray department. So you're going to have one department that's low cost, more basic X-ray equipment. And you have another department that has very, say, costly X-ray equipment that's high cost. Now you're a doctor and the patient comes in, right? And as a doctor, you try to make a prediction of the likelihood that this person has pneumonia. If you think it's low likelihood, you would send them to the low cost department. And if you thought that there was high likelihood, you'd send them to the high cost one. Okay. The problem is these departments use different, models of the X-ray machines. So when you get your data, it turns out that almost every instance from the low cost one is a negative, not pneumonia. And almost every instance from the high cost one is pneumonia. So it's totally skewed. And of course, how they take the images is not identical. That sort of framing, that's your view. And what happens in the early days is the models were learning the view, not the X-ray. Okay. And it's also known as an unseen covariant. Okay. We have all kinds of ways of trying to deal that. First, you have to detect the existence of that. So we might use a surrogate model. Okay. So if we have suspicion that, let's say, feature X is a bias or an unseen covariant. Okay. So you have your regular model you're training and you're predicting. And what I might do is, it's not that I remove the feature, is that I will, on a prediction level, I will intentionally invert that feature. And what I want to do is look at the outcome of the prediction. What I'm looking for, if it is not a bias, then the change in the outcome should be random. That is, it should not have any effect. But if, on the other hand, is not random, then I know, it's injecting some bias. So now I got to look at a wide variety of techniques to remove the bias. Big one I see being used are GANs, for example, other means of generating synthetic data. Previously, years ago, people tried to use boosting. The problem with boosting is you're adding so many identical examples that models tend to be over-parameterizing. You're really increasing the likelihood of memorization in the model.
That brings us to the work that you're doing right now of the book that you're writing to try and encapsulate some of the lessons that you've learned and the knowledge that you're sharing right now of some of the useful patterns and practices for how to go about working with deep learning and building these models. And I'm wondering if you can just give a bit of an overview about what your goals are for the book and how it is that you decided to go down the path of writing the book and starting the project.
Kind of an interesting road. I would say I started to teach, I would call it be more data science. So more classical machine learning, probably back in 2016. And most of the people I was teaching, came from the math statistical world. And then I'd say about mid 2017, deep learning, it was a big hype. Okay. And I really saw a demographic change in the students. A lot of them were software engineers. They weren't statisticians and math people and that. We don't do stats. We program. And so, you're trying to teach them this stuff and it just goes over the head. And so I had to learn somewhere in this process of stumbling how to teach to that target audience, I realized that I had to reframe everything in deep learning in the concept of a software engineer. What are their terminologies? What are their methodologies? What are their best practices? And how can I fit deep learning into that? So I did that for a number of years, and my courses got really popular. Today, I teach vast numbers of software engineers, not data scientists, do machine learning. And this book, you could say, is sort of my compilation of all those experiences of how to map this, what was once a very statistical PhD type of world, into your rank and file software engineering world.
And in your experience of making that translation from your experience with your mathematical and statistical background into the parlance of software engineers and the problems and what their priorities are, I'm curious, what were some of the more interesting ways that you had to reframe things, or some of the interesting sort of misconceptions or biases that the software engineers had coming into this space of a very mathematically oriented field?
Well, they all thought you had to know what gradient descent is, and I never teach gradient descent. I'll start with that. Early in my career, I was a software engineer in the 1990s, and there was a sort of a groundbreaking book, Design Patterns in C++ by the Gang of Four. It's really what started the whole concept of design patterns in software engineering. And so I was that concept already, programmed into me. And I did early on come to the realization to teach this to software engineers, you're going to have to define the design patterns. Now, that doesn't mean they weren't there. The problem is it was all sort of scattered across seminal research papers. Okay. And each researcher invented their own words. Many times, two different papers could be talking about practically the exact same thing, and their terminology is totally different. And their diagrams, how they draw it, totally different. So a lot of it was first identifying where all those bits and pieces are in the research papers, finding what's the most common terminology, then solidifying it so you're always talking the same, even if the paper says it differently. And then really coming down, mapping all those architectural and DAGs and that into a more common set of diagrams that could be uniformly applied to any of these models and research papers. And you see that in the book. I use a sort of an overall, you say DAG framework description that we call idiomatic. And so one of the nice things about the book is no matter what model architecture you're looking at or what DAG deployment process, it's in a consistent style of diagram. You don't have to learn one style from another.
And as far as the sort of identifying those common patterns and best practices across the different research and throughout your own experience of working in the space, I'm curious how broadly those lessons have been learned in the industry, or if it's something that you still see as being very nascent and something that everybody has to kind of discover and learn about on their own.
I would say in the last couple of years, at least in the research field, there's been a lot of consolidation, terminology and representation. It's not the Wild West anymore.
And then as far as the actual tooling and practices and infrastructure around deep learning and machine learning and bringing it into production contexts, I'm curious what you see as some of the most useful advancements and some of the areas that are still under-supported or underrepresented as far as the overall life cycle of going from idea to delivery.
I think a big contribution is really the growth of how to augment the training using unlabeled data or noisy data that's crowdsourced through a variety of what we call pretext tasks. You're not learning a task like a classification or predicting the value of the house. You're learning a transformation. So I have input X and I've defined some transformation function, f of X. Okay. And, that's a static function. So I can actually put the data into it, get what the transformation was, and use the transformation as the label. Okay. And so I'm trying to force the model to learn essential features in that latent space before I actually do the training on labeled data, which is expensive. Okay. And so, there is the opportunity. I've seen a lot of growth that we can start creating models to solve more and more problems that it would be a cost challenge for data. Another area that I see, again, improvements on data is, again, data costs money. So let's say you go into fintech, okay, maybe you're trying to do a model for fraud detection, okay. Well, you might actually have not 10, 20 fields in your structured data. You might have hundreds of fields. Okay, you don't know which ones are the good ones, right? But every one of them has a cost, data acquisition cost. Okay. And so before you would try to figure out which ones actually contribute or how well to the outcome doing a PCA analysis. But, on that scale, that's highly expensive. So one of the, with the growth of explainability, being able to instrument your model and directly attribute a prediction back to the feature list is really showing a great promise to substantially reduce the cost of identifying how my data contributes to the outcome. And as you know, a business manager make cost-effective decisions on data acquisition costs.
And in terms of the explainability advancements, I'm curious what your thoughts are on how that's going to influence the overall sort of state of the art of being able to build these models and identify useful data at the outset to be able to build more effective models downstream, and if there are any sort of potential optimizations or performance improvements in terms of the actual time to build and deliver these models because of the fact that there is more explainability that then contributes to a better understanding of how the model is actually coming to these different conclusions.
Just the whole idea of explainability implies that there will be development production improvements. I mean, let's say we have no explainability and the model's just a black box, right? We throw it out there and we have some outside observation. Okay, it's not quite what we want. And so we make a guess of what's happening inside the black box, just one notch above random, right? It's an educated guess, and then we throw another one out and we make an observation. We see how far apart those observations are. We make another educated guess. Compare that to, it's not a black box anymore. I can look inside and understand why it's doing that, and now I can do something better than an educated guess. So the number of iterations, just the nature of it, would dramatically reduce.
We've all been asked to help with an ad hoc request for data by the sales and marketing team. Then it becomes a critical report that they need updated every week or every day. Then what do? Send a CSV file via email? Write some Python scripts to automate it? But what about incremental sync, API quotas, error handling, and all of the other details that eat up your time? Today there is a better way. With Census, just write SQL or plug in your DBT models and start syncing your cloud data warehouse to SaaS applications like Salesforce, Marketo, HubSpot, and many more. Go to pythonpodcast.com/census today to get a free 14-day trial and make your life a lot easier. And then another interesting challenge that I've come across myself is just understanding what are the cases where machine learning or deep learning even is applicable to a particular problem, or the types of solutions that you can build with machine learning and deep learning, and being able to identify those opportunities, particularly if you have some sort of data source and you don't necessarily know what are the possibilities that I can build on top of from this. And I'm wondering how or what your experience has shown as far as the level of imagination necessary or the ability to identify useful opportunities for applying machine learning in a business or educational context.
Well, I know that when I'm in meetings or with our clients, we have business people in there, they're throwing everything at the whiteboard. They want to apply deep learning and AI to every aspect they can because they see cost savings and, production increases and so forth. And of course, that's the challenge. And, the new, to me, this is my opinionated opinion, is the new frontier is model amalgamation. Okay. And what that is, if you just kind of go back a little bit in time, we deployed single models that did a single task. Okay. But that by itself is not an application. And so you would have that big application on a server, like written in Java, and here and there is making out a call to a model, like the model is assisting this much bigger application. In model amalgamation, can you take essentially every aspect of that application and convert it into a model paradigm, and then connect all those models together on their own graph, and the models become the whole application? And so we're definitely seeing attempts in large companies of how to re-architect and redesign these applications so they're entirely model amalgamations.
Digging more into some of the design patterns and best practices that you're covering in the book, I'm wondering if you can give a bit of an overview about what types of problem domains they're applicable to, some of the decision factors or signals that go into identifying when to use which problems, or how you decided to break them down and which patterns to include as far as their broadest applicability for people who are trying to get into the space.
Much of the book actually cover the seminal models. Those models vast majority were, designed, you could say, before there was any kind of design pattern. So not only do I explain what's happening inside the model, I show how to reverse map that existing seminal model into a modern design pattern. Okay. And then, show the pros and cons and how it improved the science from the last one. It's hard to say to really answer your question because there's all kinds of model architectures out there. Okay. They're continuously improving. Okay. My book mainly focuses on computer vision. Okay. And one could make the argument that if you're doing a regressor or a classification, just use an efficient net. Sometimes it comes down to that. But the reality is we're doing a lot of other things like object tracking and video, poise detection, getting landmark points on the body, maybe doing instance segmentation or just semantic segmentation. And these take different types of model architectures work better because of what ends up in the latent space. And it generally involves the concept of feature reuse, or if you're talking about the natural language world, what to pay attention to. So, what Transformer has this concept of an attention head that tells later parts of the model this text or this transformation, this part of the text, is more important than the rest. Same thing in imaging, okay? I always kind of humor, in the seminal paper on the Transformer. Some of them might know that as the original model is the BERT model. The paper was called Attention is All You Need, okay, which really started a whole new era. We didn't need recurrent neural networks anymore to solve the problem. So, yeah, an analogy I would make, again, I'll just use natural language processing. What I really mean by essential features. Let's say I had a document, several pages long, and then I had a summary of that. I would want it, if my model really was correctly trained on essential features, I could take both the long form and the short form and still get the same prediction. Okay, and that just means that my model has to learn what's essential, what to pay attention to, and just as equally, what to throw away.
As you were figuring out what to include in the book, because of the fact that deep learning and machine learning is a space that is seeing such rapid evolution and so much attention, I'm curious what your challenges were of figuring out what to include and what to sort of optimize for so that the book remained useful for a longer period of time rather than having to rewrite it every 6 months because of, new research or changes in the space.
That's a nail you hit on the head there, I have to admit. I had to make that decision. How far did I go in describing seminal papers, and then make the switch, how to apply this into production? And you will find that about 2/3 of the way through the book is where that switch happens. And I say, okay, I'm not going to try to teach you any more seminal stuff. I'm just going to show you now how it's actually applied into production.
Yeah, it's definitely one of the perennial problems with any sort of technical resources. How long is it going to remain valid for? And then for people who read the book, what are your overall goals as far as what they're going to be able to take away from it, and what other background knowledge they're going to want to have coming into it, or what capabilities they'll have coming out of it after having read the full thing?
In our reviews, it's been, our pre-review is really good. A lot of data scientists have read it, even though they're not the target audience. A lot of them mentioned that, they had a gap, and the way the book explained it was really helpful for them to fill in that gap. But the primary audience is software engineers. Our goal is to sort of demystify the whole process for the software engineer and teach them how to reframe it in their world as design patterns, be able to take what they've learned here and practice and start applying it in the workplace.
And then as far as your own work of being in the space and building deep learning models and teaching other people how to move into this particular area of the industry, what are some of the aspects of deep learning and machine learning and data management that are, requisite for building these models that you see as being continuing challenges that you would like to see addressed more directly?
Yeah, well, again, let's roll back the clock a little bit to 2016, 2017. We kind of really thought of this as a serial process. Get the data right, train the model, make a prediction, evaluate it. If it looks good enough, make a prediction, kind of like the Kaggle thread. The real world doesn't look anything like that. It's very dynamic. We're continuously training. We're continuously evaluating. We're scaling these models. And so to me, all the challenges are substantially shifting into production. This is now where you get the phrase ML operations. If anything, that area job-wise is growing much faster than, say, research and development is. Okay, so just for the audience, for you Swedes who are thinking about entering into the space and where into the space, there's vast employment opportunities in machine learning operations. But the thing is, it has similarity to DevOps in that you have lots of moving parts. And it's complex, and there isn't a perfect way for all these parts to come together. And so you have to use your ingenuity of how to put the parts together, how to monitor it, and debug, and whatever issue comes up, how to address it. And it's not a boring job. You're on the go every moment.
And in your own experience, and as you continue to work in the space and help educate others, I'm curious, what are some of the areas of research or, areas of focus either in the industry or in sort of upcoming architectures or capabilities that you're particularly interested in or keeping an eye on?
When I see something that's been going on for a while and then something in a shift in another area. So let's talk about what's been going on for a while. This understanding of the distribution of weights in your model and how it affects not only how good the model is, but how big your model has to be. Okay. We looked at models because this stuff was random and some of it part of the model learned better than other parts. You needed a lot of redundancy. And so you have this, what we call overcapacity in your model in parameters. And of course, the problem with overcapacity is it opens up the door to parts of the model just memorizing data. And so we throw in all this regularization, this noise, trying to stop it from happening. But the better and better we can find ways to get the right initialization. There's actually a well-known paper on this called the lottery hypothesis. That is, get the winning ticket on the weight initialization. We can start training what we call compact models. These are models that are a lot smaller. They don't have the overcapacity for memorization. We don't need as advanced regularization techniques on them. Okay. And when deployed, they'll be more compute and time efficient. So that's one area. Okay. In the area of automatic learning, historically, whatever system we use to propose one model, train it, then propose another model and train it, you were comparing model to model and making a decision what the next proposed model is. And so there was a one-on-one, and about a year ago, some pretty good work on what's called distribution spaces for models. So again, where distribution comes in. So having a sort of an architecture instead of taking one model is sort of taking a framework for a model architecture and make a whole bunch of variants of that model architecture, do low epoch training, and then map out the results across that, say, entire set, maybe 500 models, and that's a distribution, okay? Then do that with another totally different model architecture. Don't do model-to-model comparison. Do the same thing. Make about 500 variants of it, random variants if you want to. Map out their distribution and compare the distributions and use that to define eventually what the best search space will be to find a good model. So I find that it's an evolving area. I just found it interesting because, once again, distributions. That obscure field I just happened to learn a long time ago.
Yeah, there's the perennial problem of, I never used what I learned in school. Well, at least in your case, eventually you did. Maybe not immediately, but it's come back around. And as far as working in industry and building models in education and in your current role, I'm wondering what you have found to be some of the most interesting or unexpected or challenging lessons that you've learned while working in the field and writing the book, and also if there are any patterns or practices that you have come across in your own research that you think should be more widely adopted that has so far been, either overlooked or underutilized.
Well, I think you just go based sort of on my current role at Google. I interface with what we call enterprise class customers. So they're very large companies, corporations, multinationals. And a lot of the struggle really continues to be what the model sees versus what the model was trained for. Okay. And how to not necessarily come up with new model architectures, but how to get those models to better generalize into a population that you really can't train it for.
As far as people who are looking to get into this space and want to be able to learn more after they've finished your book, what are some of the other resources that you recommend they dig into to help them be more effective at building and running production-ready models or being able to dig deeper into the existing literature?
This is one area where I may be a little bad. It's been years since I've really read books or blogs on deep learning. I just read research papers. I'm a scientist, and I'm your average software engineer. Unless you came up as a scientist, you're not going to be able to parse these papers. But I do look at, both O'Reilly and Manning, recent publications. There definitely has been a significant shift in other authors framing deep learning away from a statistical description to a software engineering description. And what I would do is I would just start looking at these books and the reviews and see how well, software engineers really feel that particular book is instrumental in educating them.
Well, for anybody who wants to get in touch with you or follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this is one that I believe I've picked before, but it's worth calling out again, particularly given the context of this conversation. And it's the book Designing Data-Intensive Applications by Martin Kleppmann. So it's sort of adjacent to the machine learning space in that it talks a lot about the sort of data management aspect and being able to build the systems that provide access to all of the data necessary to train these models. But just a very well-written and well-structured book to be able to learn more about some of the principles that go into those types of systems. And so with that, I'll pass it to you, Andrew. Do you have any picks this week?
The weather has just been great around here. Last weekend, I was up in the mountains and plan to go to the mountains again this weekend. So my pick is enjoy the great weather in the outdoors.
Definitely always a good recommendation and something that we all need to be reminded of occasionally. Thank you again for taking the time today to join me and for the work that you're doing on the book. It's definitely an interesting problem domain, and I appreciate you helping to condense some of your knowledge into a form that software engineers are able to take advantage of, and for you taking the time today to help me learn more about the problem space. So thank you again for all of your time and effort, and I hope you enjoy the rest of your day.
Thank you for inviting me.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.